This
Start the
conference will
session.
now be recorded.
In the previous class, due to some inconvenience, we had to stop the class somewhere in the middle. So we were discussing things with respect to, I would say, the clock input output. So we were seeing how to implement a LED dimmer application. So we tried generating a modulated waveform at RD0 pin of the microcontroller. We saw how the waveform is being generated, and we saw the output in the oscilloscope as well. We initially saw that we made the modulated waveform to glow with initially 50% duty cycle, and after that, after 50% duty cycle, whenever switch 1 was pressed, the duty cycle was increased, and switch 2 was pressed, the duty cycle was decreased. So that is what we discussed in the previous class. Then we got to know a disadvantage of the this particular way. We got to know the disadvantage of this bit banging method. So that is, whenever we are going with the modulated waveform to be generated with the help of the bit banging method, we got to know that after the pulse width modulated waveform is being generated, so if we have some other logic to get executed, so here for the sake of just to show you, I got a blocking statement return, but assume there are some other set of statements to be executed after the modulated waveform has got generated. So when we have certain other operations to be performed, we got to know that this modulated waveform gets disturbed if there is some other operation to be performed afterwards. So bit banging way of generating the modulated waveform is possible or can be considered only when you have got one operation to be performed throughout the bit banging method. So if you want multiple other operations to be taken care of and you have to use the bit banging method, that is quite challenging. So whatever logic you're going to write after the modulated waveform gets generated is going to disturb the modulated waveform which gets generally generated. So in order to avoid this disadvantage of bit banging method, so we are going to start with another way, that is nothing but with the help of built-in block, we will be generating a modulated waveform. Now, as we got to know yesterday, we started with the configuration of the built-in block of our microcontroller, the PIC16F8778. So it has a common block or a common module called as the CCP module. So CCP stands for Capture, Compare and PWM module. So all the three modules are being commonly taken, and we are focusing on only the pulse width modulation module. Now we got to know that. So in case of pulse width modulation, it is going to give me a modulated waveform generated at which pin of the microcontroller? At which pin will we be able to see the output? Forgot? Yes. So it is at the RC2 pin of the microcontroller. So at RC2 pin, we will be able to observe the output. There will be a modulated waveform generated of required frequency of required duty cycle at RC2 pin of the microcontroller. So it is necessary that to see the output at RC2 pin, the TRIS C2 has to be treated as output. So that was the first initialization to be done here. Now see, in the main function, when I'm calling the init config function, the first thing I'm doing is the initialization of the digital keypad, because whenever I press the switch 1, I have to increase the duty cycle. I press the switch 2, I have to decrease the duty cycle. So I'm using the same logic, but instead of having the modulated waveform generated by ourselves at a particular pin, I'm going to see a modulated waveform generated at the RC2 pin of the microcontroller. So next I have to do the initialization of the PWM, which is written in a separate .c file, that is pwm.c file. Now the very first step I'm going to write is tris C2 is equal to 0. So the reason of me having this tris-C2 return with the value 0 is I want RC2 to be treated as output. Okay, so that was the reason why we wrote tris-C2 with the value 0. Then after that, I had to select the pulse width modulated waveform like mode. So PWM mode, pulse width modulation mode has to be selected. So that will be selected by CCPXM3 to CCPXM0, and I have to write it with the value 1, 1 and don't care. Okay, so it is 1, 1 and a don't care. So X and X. So you can either have it return with a 0 or you can write it with a 1. X and X doesn't mean you are supposed to write an X. So what I am going to do here is, so this CCP1 con register is bit accessible as well as byte accessible. So you either can write CCPXM3 with 1, then CCPXM2 with 1, CCPXM1 with a don't care bit, CCPXM0 with a don't care bit. Now instead of me having it return like this, anyways, the first two bits of CCP1 con register is an unimplemented bit. So I'm going to have it initially return with the value 0. I will retain the value 0. Then CCP XX and CCP XY are also used for the PWM module itself. But initially that is also returned with 0 and 0. So I'm going to retain that 0 and 0. So I have to write CCPXM3 and CCPXM2 with 1 and 1. The other two bits are don't care bits. So that don't care bits, let me have it return with 0 and 0. Okay, just for my operation, I'm having it return with 0 and 0. Now, can you tell me what should I write my CCP1 con register with? So what is the hexadecimal equivalent? 0x. So this is 0, 0, 0, 0. So that is 0. Then 1, 1, 0, 0. That is C. Okay. So 0x00, 0x0C. So this is 0, this is C. This is 12. Yes, it is C. So when I write CCP1 con register with the value 0x0C, what happens is I'm going to select the PWM mode. So that is what we have done here. CCP1 con is written with 0xC0. So that is to select the PWM mode. Are you getting this? Okay. Now after that, when you are configuring the PWM module, now it is important that if you want a modulated waveform to get generated, you have to specify the frequency at which the modulated waveform has to get generated. Also, you have to specify the duty cycle at which the waveform has to be generated. Now, in order to specify the period, PWM period, the PWM period is specified by writing to the PR2 register. Okay. Now, remember and tell me, where do you find this PR2 register? Where do you find this PR2 register? Do you remember where we use this? Yes, it is a register. It's a special register in the timer 2 module, right? So I am supposed to specify whatever period I want. I have to write a specific value to the PR2 register. Now, can you remember and tell me how much is the maximum value I can write into the PR2 register? Yes, the maximum value I could write to the PR2 register is 255. Okay. Now, whatever period I want to specify, I have to write it into the PR2 register. So, according to our knowledge, we can have PR2 return just with a maximum of 252. So that doesn't mean the period you are supposed to write should remain below 255. So for whatever period you want to get generated, here is a formula. You have to use this formula and write PR2 register with a specific value for a required period. Okay, for a required period. The PR2 register value varies from 0 to 255. You will get any value ranging from 0 to 255. So for the required period, PR2 register has to be returned with a value. Now let me copy this formula. This complete module is in fact, you have to do some calculations. So if you are good at mathematical calculations, then you will get through this. Okay. So this is the formula. I'm just copy pasting it here. Okay. Now coming to the formula here. Okay. So this is the formula. So this is nothing but multiplication. So this is multiplication. This is also multiplication. Why for PWM we are using timer 2? I mean PR2 only. Okay. Now if you remember, there was a feature of timer module. Okay. So if you remember, one of a feature of the timer module said you can use the timer for generating the pulse width modulated waveform also. Now, the only timer which supports the generation of modulated waveform is timer 2 module. So we have three modules, three timers in our microcontroller, but it's only the timer 2 which is being used. So that depends on the configuration of the microcontroller. So in case of our microcontroller, for the required period, I have to write it into the PR2 register. So maybe tomorrow you may come across a built-in block which will have to write the period into timer 1 register. So it can be anything. According to our microcontroller, so I have to write the period to the PR2 register. Okay. Now, generally, when I have to get a modulated or any waveform generated, do we tell things in terms of frequency or in terms of period? So when I have to get a waveform generated, so do I say I want a waveform of 1 hertz frequency, or I say I need a waveform of 1 second period? So which one is very commonly used? It is frequency. Okay. So it is frequency very commonly used. And what is the correlation between frequency and period? What is the correlation between frequency and period? Yes. So frequency and period are inversely proportional to each other. Okay. Now I will go with a simple example. So I want to generate a pulse width modulated waveform of 5 kilohertz frequency. Okay. So generate a pulse width modulated waveform, okay, of 5, let's say, kilohertz frequency. Okay, this is the question. So you are given with the frequency. Here is a formula for the period. So you already know that period is inversely proportional to frequency. So I will write 1 over f PWM. So that is frequency of PWM, which is equal to, so this formula I have to retain as it is. So PR2 plus 4 plus time of oscillation we don't know. So I can write period of oscillation. I mean time of oscillation is 1 over frequency of oscillation. Okay. Plus TMR2 pre-scalar value. Okay. Now do the calculation. Assume I'm going to use a pre-scale of 1:4. Let me check what is the pre-scale. Yes. So assume I'm going to go with the pre-scale of 1:4. So you can choose what pre-scale you want to use. So assume there is a pre-scale of 1:2, 1:4. Do the calculation here and tell me what is the value of PR2. So do the calculation here and tell me what is the value of PR2. So you have to be good at mathematics here. So for a frequency of 5 kilohertz, we are trying to generate the value. We are trying to find the value which has to be loaded into the PR2 register. So we got a formula which has to be used to get the PR2 value found. So how much is the PR2 value if I have to generate a frequency of 5 kilohertz? Okay. So do the calculation later. If you want, I can substitute these things. Okay. So I can make a substitution and show you. So frequency of pulse width modulation is 5 kilohertz. Okay. Then F oscillation frequency is 20 megahertz. And TMR2 prescalar value is 4. 1:4 means for the calculation you have to use 4. Now after the class gets over, please do the calculation and cross check again. So you are going to end up getting the PR2 value as 249. Okay. So you have to get a value which ranges from let's say 0 to 255, because PR2 can be written with the value 0 to 255 only. Now, if you get something more here, then you have to make adjustments in the prescalar value. Okay, you can choose a bigger prescalar value. You can choose 1:16, you can choose 1:39, and you can choose more than that also, according to the availability of the prescalar. So in the timer too, if I'm not wrong, I think the prescalar maximum available is 1:4 itself. Okay. So in that case, you have to take 1:4 itself being the maximum. So you have certain restrictions also. You cannot get a modulated waveform of 10 kilohertz frequency, or like just one hertz frequency, something like that. So you should be careful to what write into the PR2 register. You can write any value ranging from 0 to 255 only. Anyways, now to get a modulated waveform of 5 kilohertz, I have to write PR2 register with 249. Okay, so that is what we have written here, PR2 with the value 249. That is to make sure I'm going to get a frequency generated of 5 kilohertz. Now, because I'm using the timer 2 module, it is necessary to turn it on. So I'm writing TMR2 on is equal to 1. Okay, so because we are taking timer 2 module, we have a separate bit to turn it on. So I'm writing TMR2 on with the value 1. Apart from this, I used a prescale of 1:4. So I have to set the prescalar value also. So that is written with T2CKPS1 written with the value of 0, and T2CKPS0 written with the value 1. Okay, so that is prescalar. So if you want, I can show it again here in the data sheet of the prescalar bits to be used. So that is timer 2 module. Okay, so the prescalar here you can see, in order to select a prescale of 1:4. Okay, I do have a prescale of 1:16 also. So if I want a prescale of 1:4, T2CKPS1 has to be written with 0, and T2CKPS0 has to be written with 1. So that is what we have done here. PR2 is equal to 249, T2CKPS0 written with 1, and T2CKPS1 written with 0. So timer 2 on in order to turn on the timer. So this one is to select the PWM mode. Understood the initialization of PWM? Everybody? Now, apart from frequency, what else should I be specifying? Apart from frequency, what else should I be specifying to the built-in block to get the modulated waveform generated? Yes, I also have to specify the duty cycle. Now, if you have to specify the duty cycle, you also have to write some 10-bit value to another register. Okay, so let me show it here under PWM mode. So in order to specify the duty cycle, you can see the PWM duty cycle is specified by writing to the CCP R1L register and CCP 1 con register 5th and 4th bit. Now, why do I use two registers is, so it is supposed to generate a modulated waveform of a specific duty cycle. So that is, we are using 10-bit resolution. Now, how much is the bitness of our microcontroller? Yes, the bitness of our microcontroller is 8. That means the maximum size of the register is 8 bit. Okay, so Saurabh is saying, sorry to interrupt, ma'am. I joined a little late. Can you please tell what are we trying to implement? So we are trying to generate a pulse width modulated waveform with the help of built-in block. So we wrote a period, the required period into the PR2 register. Now I have to write the duty cycle to a specific register. Now duty cycle, whatever I'm going to say, will be specified in 10 bits. And those 10 bits cannot be returned to a single register because in case of our microcontroller, the maximum size of the register will be 8 bits because ours is a 8-bit microcontroller. So if I have 10-bit value to be returned, 8 bits will be returned to the CCP R1L register and 2 bits will be returned to CCP 1 con register 5th and 4th bit. Okay, so CCP R1L register contains the 8 MSBs and CCP 1 con register 5th and 4th bit contains the 2 LSBs. So let me copy the statement and have it noted here. Okay, so CCP R1L contains the 8 MSB bits and CCP 1 con 5th and 4th bit contains the 2 LSB bits. Now, I have to find the 10-bit value to a particular duty cycle. So if my duty cycle is 50%, I have to find a corresponding 10-bit value. If my duty cycle is 100%, I have to find a corresponding 10-bit value. Now, please understand, if the duty cycle is fixed, okay, if the duty cycle is fixed, you actually can find the duty cycle and you can find a 10-bit equivalent value to it and you can have it return in the initializing function itself. But in my case, whenever I press switch 1, duty cycle is going to increase. Whenever I press switch 2, duty cycle is going to decrease. So because of that, what happens is, as the duty cycle is going to change again and again, I may have to keep writing to the two registers, CCP 1 con register and CCP R1L register. So if I write it in the initializing function, I will end up writing the register only for once. Now, because I'm supposed to write it anytime the duty cycle is going to get changed, I have to write it into the CCP R1L register and CCP 1 con register. So that is why we have a separate function written for it called as a set PWM duty. So what we are doing here in the main function is, first I'm going to read the key. Okay, that key will be passed as an argument to the PWM control. So control will come here. Now initially duty cycle is 50. 50 represents 50%. Maximum duty cycle is 100% and wait is initially 0. The logic is remaining the same if you observe. So if duty cycle is not equal to maximum duty cycle will be increased, and if key is not equal, key equal to switch to and duty cycle is not equal to 0, duty cycle will be decreased. Earlier, I was specifying the duty cycle and that was fed to the LED. This time, that duty cycle is passed as an argument to the set PWM duty function. Now, what this function does is, this function is going to write a 10-bit equivalent value. So, a 10-bit equivalent value for the required duty cycle. Okay, this is going to write a 10-bit equivalent value to the required duty cycle into uh, the two registers, CCP R1L register and CCP 1con register. Okay, so that is nothing but the set PWM duty function. Now for that also we have a formula. This is the formula I have to make use of. So I'm going to copy the same formula here. Okay, so PWM duty cycle is nothing but, this is the name of the register, CCP R1L and CCP 1con 5th and 4th position. So this is multiplication T2 T oscillating frequency, and this is pre-scalar value, timer to pre-scalar value. Okay. Now I will make an assumption. The name of the register is this, so I cannot keep using it. So assume X is equal to this. Okay. So I'm going to rephrase my formula. Okay. So this will be replaced by X. Now, according to the representation here, okay, you can see duty cycle, you know that duty cycle is nothing but the on period. Okay, so duty cycle is nothing but the on period of the pulse. Okay, so you know that duty cycle is nothing. I'm trying to simplify this formula a little. Okay, so duty cycle is nothing but, let's say, T on period. Okay, so T on is nothing but duty cycle. So according to the formula we have learned, duty cycle is nothing but T on divided by the period, PWM period, correct? So according to the formula we have known, duty cycle is nothing but T on divided by PWM period. So we have a formula for PWM period. We know what the duty cycle is. So duty cycle is nothing but T on in case of our program. So T on is nothing but duty cycle, okay, multiplied by PWM period. Okay. So now I'm going to rephrase this formula. I'm trying to just simplify this formula. So duty cycle multiplied by PWM period is nothing but X multiplied by T oscillating frequency multiplied by TMR to prescalar value. Now PWM period has a separate formula. I'm going to substitute it. So this whole formula I'm going to substitute it here. Now do the cancellations and tell me what will be left. So T oscillating frequency and TMR2 prescalar value gets cancelled each other. So I'll be left with this much on the right hand side. Okay, is equal to X. Correct? So X is nothing but D multiplied by PR2 plus 1 multiplied by 4. Now, please tell me what is the value of X for a duty cycle of 50%. So I'm passing percentage. So to reduce that percentage, let me write D divided by 100. Okay. So to get rid of that percentage, I'm writing D divided by 100. Now for a duty cycle of 50%, tell me what is the value of X? Is that 50? Are you sure? So PR2 value we wrote is 249. 249 plus 1 is 250. 250 multiplied by 1000 will be, 250 multiplied by 4 will be 1000. So two zeros cancel. So duty cycle will be 50 multiplied by 10. So if I'm not wrong, X you have to end up getting 500. Can you confirm this? Okay. Now, what you have to do is, to get a duty cycle of 50% generated, you have to write the CCP R1L register and CCP 1 con register with CCP 1 con 5th and 4th bit with 500. So can you tell me what is the 10-bit equivalent of 500? What is the 10-bit equivalent of 500? I want a 10-bit equivalent value because I'm going to write a resolution of 10 bits. So what is the 10-bit equivalent of 500? Okay, fine. So let me just copy this. Okay, so I wanted 10-bit equivalent value. I copied it from one of your texts and I pasted it here. So this is the 10-bit equivalent value. Now, I cannot write this complete 10-bit equivalent value to a single register. I have to write 8 MSBs to the CCP R1L register and 2 LSBs to the 5th and 4th bit of the CCP 1 con register. Now tell me how to write 8 LSBs to the 8 MSBs. Write 8 MSBs to CCP R1L register. Can you tell me how to write it? Can I write CCP R1L is equal to X? Can I write CCP R1L is equal to X? Is that possible? Okay, what happens if I write CCP R1L is equal to X? What happens if I do it like this? It will take all bits? No. The size of the register will be 8 bits only. It will take only 8 bits. So which 8 bits do you think will be taken by the CCP R1L register? So what should I do? Yes, last 8 bits. So these 8 bits will be taken by the CCP R1L register. I want these 8 bits to be taken. What should I do? I want the first 8 bits to get assigned to the CCP R1L register. How to bring it to the right? Have to bring it to the right. What should I do? Yes. So I have to right shift it for 2 times. Okay. When I right shift it for 2 times, this whole thing will be brought to the right for twice. So something like this, 0, 0, then 0, 1, 1, 1, 1, 1, 0, 1. So don't you think I got 8 LSBs returned to this particular position? So did I not write 8 MSBs returned to the CCP R1L register? Fine. So that was the first thing. I have to write 8 MSBs to the CCP R1L register. Then I have to write 2 LSBs, okay, to 5th and 4th bit of CCP 1 con register. How to do this? I want to write two MSBs to the 5th and 4th position of CCP 1 con register. First of all, tell me how to get two LSBs out of this. How to get two LSBs? Yes, so I have to AND with 1 and 1, binary 1 and 1. Okay, can I say 0x03? So to get two LSBs, can I say x has to be AND with 0x03? Okay, I will get two LSBs. Now I want to bring it to the 5th and 4th position. What should I do? Bring this to 5th and 4th position. Left shift for how many times? Should I do it only for, okay, 3 times or 4 times? 5th and 4th position. Position starts from 0. Okay. So I have to bring it to 5th and 4th position. Assume 0, 0, 0, 0, 0, 0, 0, sorry, 0, 0, x is what I have. I want to bring it to 5th and 4th position. How many times should I shift? I have to shift it for 4 times, right? So I have to shift that for 4 times to the left. So what? I have to shift x and with 0x03 to the left for 4 times. Now, how to write it into the CCP 1 con register? How to write it into the CCP 1 con register? First of all, do I know what is written in the 5th and 4th position of CCP 1 con register? No, right? And always a good practice is, before you write into that particular bit, a good practice is you have to clear the 5th and 4th bit. Okay, so I have to clear the 5th and 4th bit of CCP 1 con register. Now how to clear the 5th and 4th bit of the CCP 1 con register? CCP 1 con, what should I do? And with what? CCP 1 con. And with whichever position I want, I have to AND with 0. No, complement of 0x03 is not right. Only 5th and 4th position I have to make it 0. So it is binary 1 1 0 0 1 1 1 1. Correct? So only 5th and 4th position I want to make it 0. The rest I have to write it 1. So what is the hexadecimal equivalent of this? CF. Okay. So I will write 0x CF. Now I have to OR. Okay. So I have to write something like this. CCP 1 con is equal to, first, CCP 1 con AND with 0x CF. So that is to clear the 5th and 4th bit of the CCP 1 con register. Or with, I have taken the bits from the LSB and I have moved it to 5th and 4th position. So like this. Now after I perform this operation, two LSBs gets returned to CCP 1 con register 5th and 4th position. Are you following this? Okay. So the same is written here. You can see set PWM function. So unsigned register value is nothing but, register value is nothing but float of duty cycle divided by 100 multiplied by 250 multiplied by 4. So that is this calculation. Okay. So here this calculation. So D, whatever duty cycle you are going to pass, divided by 100 multiplied by PR2 is 249 plus 1 is 250 multiplied by 4. So that we have written it in a simplest way. Then to write 8 MSBs, I am writing that register value right shifted for 2 times into the CCP R1L register. Now To have two LSBs return to the 5th and 4th position, I first AND CCP1 con with 0xCF, that is to clear the 5th and 4th position. Then I AND the register value with 0x03, that is to get the two LSBs. I left shift it for 4 times, that is to make sure the bits are moved to 5th and 4th position. And I'm going to OR. So I will have CCP1 con register return with the two LSBs in the 5th and 4th position. Now that I have returned the PR2 value, which is specifying the frequency, also I have returned the two registers, I will end up getting a modulated waveform generated at RC2 pin of the microcontroller. Now observe, I'm building the project. So build is happening. There are some warnings because of these shift operations, bitwise operators, because they are supposed to be done on integers, but we are doing it on characters. So we are getting a warning. You just can ignore that warning. Okay. Now let me show you the output. So file, load hex. So built-in block, distribute, default, production, the hex file. Okay. Now you should be able to see a modulated waveform at RC2 pin of the microcontroller. So I'm showing you the output in the oscilloscope. So here I'm using the first channel only, and this time it is RC2 pin. Okay, so you may have to search for RC2 pin, RC1, RC2. Okay, so you can see, let me increase the time. Sorry, decrease the time. Okay, so can you see here, there is one pulse being generated in 0.2 milliseconds. So width of each pulse is 0.1, sorry, width of each division here is 0.1 milliseconds. So 0.2 milliseconds is what you take for a pulse to get generated. Okay, so it is something like this. In 0.2 milliseconds, there is two pulses generated. Okay, one pulse generated. Okay, so one pulse gets generated in 0.2 milliseconds. So now you can see in 1 second how many pulses is going to get generated. How many pulses in 1 second? So it has to be 5,000. Okay, because we have taken 5 kilohertz. Can you observe this? I mean, can you correlate this? So one pulse is getting generated in 0.2 milliseconds. So in 1 second, how many pulses are going to get generated? Okay, so it will be 1 divided by 0.2 milliseconds. Okay, so it is 5,000 pulses. Yes, so it is 1 divided by 0.2 milliseconds. So 5,000 pulses will get generated in 1 second. So that is what we said. So whenever initially the duty cycle should be 50%. Okay. So for a frequency of 5 kilohertz. Now if I press switch 1, the duty cycle has to be increased. And if I press switch 2, the duty cycle has to be decreased. Okay. So I press switch 1 here. Duty cycle has to be increased. You can see. And I press switch 2 here. Duty cycle is going to get decreased. I hope you are able to see this. So this way, with the help of the built-in block, you can actually make your microcontroller generate a required pulse of 50% duty cycle. Fan is on because the board is feeling the temperature is quite high. So to make the temperature, see, you can observe temperature, it says 27.5 degrees Celsius. So because the temperature is quite high, there's a fan running. Is that clear? So this completes the clock input output. So here you are going to generate a modulated waveform of required frequency and of required duty cycle. So first we saw with the help of bit banging method. The next we have seen is with the help of the built-in block. So there is one more way of generating the modulated waveform, but that is a part of your assignment in fact, and that you are going to do it with the help of timer. Okay, you can use timer module to have a modulated waveform generated at a particular pin of the microcontroller. So this completes the other next peripheral, and we are going to start with the next peripheral of the module, which is nothing but the SSD. You can take a break of 2 minutes and we will be continuing. Okay. Can we proceed? Hmm. So once the nodes you wrote. Okay. So here is the nodes I wrote. Okay. All right. So let us continue. So the next peripheral we have got to discuss in this module is nothing but the SSDs. Now, do you know what exactly SSD stands for? Yeah, solid state drive. No. Okay. I think I'm showing it directly. Okay. So SSD stands for 7 segment displays. Okay. So SSD here represents 7 segment display. Now, before I make you understand what exactly is an SSD or how does an SSD work, the first thing you have to know is why should we be learning an SSD to be used? So why not some other peripheral? And why are we supposed to use the SSD itself? Now, generally what happens is when it comes to the feedback device, okay, so we have several feedback devices. So whenever we come to the feedback device, the very commonly used feedback device is nothing but the LED. Now, what is the feedback devices? The one which is conveying something, like using which the machines convey something to the user. So we call it as feedback devices. So if the machine is conveying something to the user, so we call it as feedback devices. Using these feedback devices, they are going to convey something. Now, the very commonly used feedback device is LED. Assume I have multiple feedbacks to be given. I mean, assume the machine has multiple feedbacks to be given to the user. So some of the feedbacks can be represented like this. Now assume the very first feedback what the device has to show is, assume it has to represent some error. So assume it is a battery low. Okay. So it has to represent an error called battery low. So what the LED can be used as a, like when LED is used as a feedback device in multiple scenarios, one thing is I can blink LED for certain number of times or I can blink LED in certain frequency. I can blink LED for every 1 second to represent one error. I can blink LED in more than for every 2 seconds to represent some other error. Or I can blink LED for 5 times to represent one error. So assume battery low is indicated by blinking the LED for every uh, zero point 0.5 seconds, means half a second. For every half a second, I'm going to blink the LED to represent battery low. Assume there is another error you want to show, that is engine heated up. Okay. So engine is heated up. It has to be represented. So what the device does is, it is going to blink the LED for, let's say, every 1 second. So something like this. Now the problem with only LED being used as a feedback device is, I have to keep proper eye on the LED. I have to properly monitor at what frequency LED is blinking or for how many times the LED is actually blinking. Okay. So for certain scenarios to be represented, you have to make a keen observation on the LED. And that I feel or anybody feel is it is time consuming or it is challenging for you to see that LED is blinking for, like, you have to properly monitor whether it is blinking for every half a second or it is blinking for every 1 second. You have to properly monitor. And that is always a challenging task. Now, instead of you blinking the LED in different frequencies or blinking the LED for certain number of times, don't you think it will be good if I will be able to display some error numbers at least? So don't you think it will be good if I display error 1 like this, error 2 like this, error 3 like this, something? So obviously that will be a little easy representation. It will be a easy human feedback device if I can represent the error numbers directly. And this is the reason why we are going to make use of SSD. So SSDs can be used to have the error numbers directly displayed on them rather than getting the only LED used as a feedback device. Now coming to the SSDs here. So this is SSD, which represents 7 segment display. But in fact, if you see, there are 8 segments. So starting from segment A, there is A, B, C, D, E, F, G, and decimal point. So there are 8 segments in fact, but the very commonly used is only the 7 segments. The major concentration being made is only on 7 segment. Hence the name 7 segment display. Okay. And each segment here in the SSD is made up of an individual LED. Every segment in the SSD will be made up of a individual LED. So you can see every segment here. So each segment will have one individual LED connected to it. Now, there are two ways of LEDs connection being made. One we call it as common anode configuration. The other one is common cathode configuration. So if you take this SSD, each segment of the SSD involves one LED. So one SSD is going to have 8 LEDs inside it. Now these 8 LEDs can be commonly connected in the anode side or it can be commonly connected in the cathode side. So this is the possible configuration. Now if you see the first case, this side is anode and this side is cathode. So what type of configuration is it? In the first side, what type of configuration is it? It is common anode or common cathode. So this one is called as common cathode because all the cathodes are commonly connected to ground. Okay, so this is called as common cathode as all the cathodes are commonly connected to ground. And on the right hand side, what you see is common anode because all the anodes are connected to VDD. So they are commonly connected to VDD, hence we call it as common anode. Now, if the configuration is common cathode, what should be provided at these pins to turn the corresponding LED on? So if I have to turn on the LEDs, what needs to be provided at these pins? Assume they are connected to a pin of a microcontroller. What should I be providing? VDD. How do we represent VDD digitally? Yes, you have to be providing a 1. So if I provide 1 here, this LED is going to glow. If I provide 1 here, this LED is going to glow. So whichever LED has to be glown, it has to be provided with 1 in the common cathode, and to turn it off, I have to be providing a 0. So that is common cathode. But when it comes to the common anode, to turn on a corresponding LED, I have to be providing a 0 to turn it on and 1 to turn it off. Correct? Let me make a note of it actually. Okay. So we are talking about SSD here. Okay. And when it comes to the SSDs, so I have common cathode configuration Okay, where all cathodes, I would say cathodes of all 8 LEDs are commonly connected ground. Have to come to 0. Okay, fine. So I was telling, in case of common cathode, cathodes of all 8 LEDs are commonly connected to ground. So to turn on the LED, to turn on LED of a corresponding segment, okay, so we have to be providing a 1. Okay, provide a 1. Similarly, to turn off LED of a corresponding, can somebody turn on Lokesh? So Lokesh is like creating again, muting him again and again, he's doing the same. Okay, I removed him from the meeting. That is the least I could do. Okay, to turn on the LED of a corresponding, okay, to turn on the LED of a corresponding segment, I have to be providing a 1. And to turn off the LED, okay, to turn off LED of a corresponding segment, I'm going to provide a 0. So that is in case of common cathode configuration. Okay. Now, similar to common cathode, I also have common anode configuration. Okay. So this is common anode configuration. Anodes of all 8 LEDs are commonly connected to VDD this time. And to turn on the LED of a corresponding segment, I have to be providing a 0. And to turn it off, I have to be providing a 1. Okay. So that is SSD. So after that, what else we have? If you look at this, LED is nothing but, SSD is nothing but an array of LEDs connected internally. The possible configurations are common anode and common cathode. Now, the biggest advantages of using the SSD is it has a very good line of sight. So, good line of sight in the sense, even being in a farther distance, you will still be able to identify what exactly is being displayed. So that is one of the biggest reason why SSDs are commonly used. Can you tell some of the applications where SSDs are used in our day-to-day life? Uh, can we turn them on off using hexadecimal values? So that is with the help of a complete port. If all the 8 pins of the SSD is connected to a one particular port, then you can use the hexadecimal value to turn it on. You will see it after this. Okay, you can see it in watches, okay, calculators, gas stations, digital clocks, right? And where else? Petrol bunks, okay. Wall clocks, fine. Meter boxes, lifts, right. Railway stations, right. So washing machines, right. Traffic signals, right. Railway stations, right. Yes. So we can see SSDs in so many places. Okay. So the very biggest disadvantage of it is, in fact, it has a very good line of sight. So that is the biggest advantage. Now, assume there is an SSD. Okay. So this is the SSD. If you see on our board, how many SSDs do we have? Can you look at this board and tell me how many SSD do we have? Yes, we have 4 SSDs. Now, if I take 4 SSD, in each SSD, how many lines do I have? I mean, how many LEDs do I have in each SSD? I have 8 LEDs in each SSD. Okay. Now, to turn on 8 LEDs individually, how many input lines do you think I need? To turn on 8 LEDs, how many input lines do I need? I need 8 input lines. Okay. I need 8 input output lines to turn on 8 LEDs. Now, if I have 4 SSDs, can you tell me in total how many lines do I need to turn on individual segments of these SSDs? I need 32, right? So 4 multiplied by 8 is 32. So I may need 32 lines to turn on the LEDs of each segment. Now tell me how many input output pins do I have in my microcontroller? A total of how many input output lines do we have in PIC16F877A microcontroller? Come on. Do you remember how many input output lines we have? Yes, it is 33. Now out of the 33 input output lines, do you think it will be good for me to use 32 input output lines just for configuring an SSD? Obviously no. So that will be a foolish decision of anybody to use 32 input output lines just to configure a single peripheral. So what we did was, we have made a configuration like this. I mean the board, the simulation board has got the configuration made like this. So all of the 4 SSDs are commonly connected to 8 data lines. So assume something like this. All the segment A is connected to one line. All the segment B is connected to another line. Segment C, segment D, segment E, segment F, segment G, and segment DP. So all of these have been connected in common to only 8 data lines. Segment A of all SSD is connected to one data line. Segment B of all SSD is connected to one data line. Segment C of all SSD is connected to another data line this way. Now think and answer. Anything I'm going to provide here. For example, assume I have a common cathode configuration. To turn on the LED, what should I be providing in common cathode? I have to be providing a 1. Assume I provide a 1 here. Okay. Tell me which SSD's A segment is going to get turned on? Which SSD's A segment? Yes. All 4 SSD's A segment is going to get turned on, right? So don't you think all 4 SSDs are going to get the same thing displayed? Okay. Now anything I provide here, don't you think it will make all 4 SSDs display the same thing? Yes. So whatever I provide here, so I say, let's say 1011. So I'm randomly giving some data, 1011. Then assume 0001. So that is what I'm providing to the 8 pins of the microcontroller. Now if I provide something like this, that gets reflected in all 4 SSDs. Now do you think I will take multiple SSDs to display the same data? Do you think my intention of taking multiple SSDs will be to display the same data? No. So my intention obviously will be to display multiple things at once. So I don't want all SSDs to display the same data. So that is why when you make the connection like this, if the hardware connection is made something like this, it is going to show the same data on all the 4 SSDs. So for me to display different data in different SSD is not at all possible if the connection is made something like this. Now how to solve this problem? So this problem can be solved by having 4 different control lines. Okay. So I'm going to have control lines taken. Now what is the task of the control line is, whichever SSD I want, I will turn on only that SSD and I am going to provide the data. Okay, whichever SSD I want to turn on, I'm going to provide the data and I'm going to turn on those. Observe, we will have a control line provided like this. Okay, now here what happens is, you will either have common cathode configuration or you will have common anode configuration. In common cathode configuration, what needs to be provided in common? In common cathode configuration, what needs to be provided? What needs to be provided in common? Yes, it is ground. Ground should be provided in common to every LED. Now, only if you provide ground to a particular SSD, that will allow the data to get reflected. So assume I write 0, 1, 1, 1. So to which SSD am I providing the ground? Assume it is a common cathode configuration. So to which SSD am I providing the ground? So it is to the first SSD. Only to the first SSD I am providing the ground. So for the rest of the SSDs, I am not providing the ground. Now if the ground is not provided in common, do you think the other SSDs are going to get turned on? Do you think other SSDs are going to get turned on? No. So I am considering a common cathode configuration where I have to provide, let's say, I have to be providing ground in common to all 8 LEDs of a corresponding SSD. Now, only if the ground is provided to the SSD, that SSD is going to get turned on. So if I don't provide ground to a corresponding SSD, I don't frame a common cathode configuration and I will not be able to get the LED turned on. Now assume I'm going to write 1, 1, 1, 1. Okay, at some point of time, I'm writing 1, 1, 1, 1, 1, 1, 1, 1. Okay. Now which SSD is going to get turned on? Which SSD is going to get turned on? First SSD. And which segments gets turned on of the first SSD? Which segments are going to get turned on of the first SSD? All 8 segments of the first SSD is going to get turned on. Am I right? Yes. All 8 LEDs of the first segment is going to get turned on. Now there is a small problem. I am providing the ground to a particular SSD at a particular pin of the microcontroller. So when I provide one to all of the segments like this, the current via the segment cumulatively will flow to the microcontroller. If you observe, there is segment A. Okay, so current from segment A flows to the ground. Current from segment B, segment C, segment D, segment E, segment F, segment E, and segment DP. So current from all the LEDs will go cumulatively into my microcontroller. Do you see that? Do you understand what is happening? Yes. Now what happens in this scenario if 8 LEDs power is cumulatively moved into a particular pin of the microcontroller? What happens? So it is going to damage that particular microcontroller, isn't it? So I will get the damage to the particular pin of the microcontroller. This is going to damage the particular pin of the microcontroller. Now what is the solution to this? I have to be providing the ground. Now keeping one resistor is not possible. Okay, keeping one resistor will not generally help me use all the load. Yes, so I can use something which acts like a switch. Okay, so I'm going to use something which acts like a switch. A good example for that is something called as the MOSFET. Okay, so you can make use of a MOSFET. So like this, if I provide 1 and provide a 0 here, So segment A of the first SSD is going to turn on and current is flowing to the ground. Okay. Now what I'm going to make use of here is so MOSFET or transistor. So if you pay attention here, if you properly notice uh, the transistor I have taken is in fact which one? So it's a NPN transistor. Okay. So it's a NPN transistor. Now I am going to provide ground with the help of a NPN transistor. Now observe. So this is one of a pin of the microcontroller. Okay. So I provide one. Let's say one. So I'm providing one to all the pins. Okay. In market there are a lot of 7-segment decoders are available. I understand. So like in the markets everything are being advanced. So I'm not saying it is not possible. So we are talking about SSDs which is available on this board. You should have a basic ideology of how SSD is actually been working. So that is the idea behind we discussing SSD this way. Okay, so I provide one here. So I want the cumulative current to be flown to the ground here. For that, I have to turn on the corresponding transistor. Okay, so via the transistor, I'm going to provide the ground. You can observe here, I'm providing ground to the SSD via the transistor. So what do you think should be provided to the transistor to turn it on? What should I be providing to the transistor to turn it on? So I have to be providing a 1. Okay. If I provide a 1, the corresponding transistor is going to turn on. If I provide a 0, the corresponding transistor is going to turn off. Now look at this and tell me, if I provide 1000, which SSD is being provided with ground? If I provide 1000, yes, it's the first SSD which is being provided with ground. The transistor is turned on and it is giving you the ground connection. So whichever segments gets turned on, so that happens depending on what is provided at these pins. So whichever segment gets turned on, its cumulative current flows via the SSD, via the transistor to the ground like this. So, for example, whatever I want to display, I can provide here. Okay, anything I want to display, I can provide the data here. And to select a particular SSD, I have to be providing the value here. Now tell me, if I want to display something on display 3, okay, I want to display something on display 3. So what should I be providing here? If I want to display something on display 3, yes, I have to give a 0010. Okay, so I have to be providing a 0010. So providing 1 here will turn on this transistor. So that is going to provide the ground. So anything you provide here will be accepted by display 3 and the cumulative current will flow to the ground via the transistor 3. Okay, so if you can observe here, this is in fact the circuit which is available on board. So segment A is connected to RD0, segment B is connected to RD1, RD2, RD3 and DP is connected to RD7. So port D is connected to the 8 segments of the SSD. RA2, RA3, RA4 and RA5 are used for the control lines. Okay, so RA2, RA3, RA4 and RA5 are used for the control line. Are you getting this? Okay. Now observe this. I'm going to show you one representation. So please pay attention here. Okay. Observe this. Assume it is a common anode configuration. Okay, it's a common anode configuration. So in case of common anode configuration, what needs to be provided to turn on the LED? What needs to be provided? 0 to turn it on. Okay, in case of common anode, you have to be providing a 0 to turn it on. And okay, so this time you have to actually provide VDD in common. Okay, so you have to provide VDD in common. Okay, now observe here. Okay, observe here and tell me which SSD is going to display what. So in the first scenario, so assume providing one here is going to give the common VDD. Okay, so providing one here is going to provide the common VDD. So if it is C2 provided with one, which SSD will be selected? If it is C2 provided with 1, it is second SSD. And C3 provided with 1, it is the third SSD. Now tell me what gets displayed on second SSD and what gets displayed on third SSD. Consider it as a common anode configuration. Okay, 2 gets displayed on second SSD. And what about the third SSD? Yes, 5 gets displayed. Now see what happens in the first scenario. Okay, so 0 is going to turn on that particular segment. So in case of first scenario, A is provided with 0, then B is provided with 0, C is skipped, D is provided with 0, E is provided with 0, then F is written with 1, then G is provided with 0. So you will get 2 displayed on the second SSD. Coming to the third SSD, 0 for A, it is going to get it turned on. B is not returned. So C is 0. Then D is 0. Then E is 0. Sorry, E is not there. F is 0. And this is 0. Okay, please ignore this E. I wrote it by mistake. So 5 has to be displayed on the third SSD. So you can observe here. Okay, so 2 gets displayed, then 5 has to be displayed. Now the problem is I want 2 to be displayed on the second SSD. I want 5 to be displayed on the third SSD. Now in order to display 2, I am going to provide this data and turn on the second SSD. In order to display 5, I will provide the data here and I am going to turn on the third SSD. You can see here, to display 2, I provide data here from segment A to segment DP. Then I'm going to turn on the second display. To display 5, I'm going to provide 5 here. Okay. And I am going to turn on the third SSD. Now there is a problem. I want 2 and 5 to be displayed on a constant manner. Okay, 2 in display 2, 5 in display 3. So how do you think I'm supposed to do it? So as of now, I'm providing the data for 2, turn on the second SSD. I provide the data for 5 and turn on the third SSD. How do you think I will be able to write? I will be able to show both 2 and 5 together. Actually, something like this. I don't want to see the toggling. Yes, I have to write it faster. I have to do it. I have to increase the frequency. I have to write it in such a way that our human eyes will not be able to see that switching between the SSD. So give the data for 2, then turn on the second SSD. Give the data for 5, turn on the third SSD. Do this on a very faster manner. So something like this. So do it on a very faster manner that at some point of time, our human eyes will not be able to identify the switching between the two. Okay, so you have to keep the frequency more. So you have to give the data to print to, then you have to turn on the second display. Give the data to print 5, then turn on the third display. Now do it on a very faster manner that our human eyes will not be able to see the toggling between the two SSDs. Okay, so that is nothing but SSD in general. So SSDs are like, basically the working principle of SSD is very same associated to that of an LED. You just have to know how to make different data displayed on different SSD. So you can see the circuit on board. So this is how the SSD has been available on board. We have 4 displays. So each of the segments varying from segment A to segment DP is connected from RD0 to RD7 pin of the microcontroller. And if I have to select a particular SSD, I have to use the control lines varying from RA2 to RA5. Okay. Now we will make a small table for our convenience. So I have 8 segments varying from A to DP. Okay, so A to A, B, C, D, E, F, G and DP. So I have 8 segments connected from RD0 to RD7. It is our luck that I have port D completely utilized for the 8 segments of my SSD. So RD7, I'll go with RD7 first. Okay. Then RD6, I'm noting down the pins. RD5, RD4, then RD3, RD2, RD1, RD0. Okay. So these are the 8 pins. Now tell me, I am going to, I want to display 1. Okay. So these are my 8 SSDs. Let me say. So my SSD is something like this. Okay, so this is my SSD. So consider DP also. This is segment A. This is B. This is C, D, E, F, and G. Okay. Now tell me if I have to display 1. Okay. So I'm going to display 1 something like this. If I have to display 1, what should I be providing here? Which corresponding SSD has to be turned on? B and C. And in our case, it's a common cathode configuration. So 1 will be displayed in B and C, and ours is a common cathode configuration. So the rest of the things have to be provided with 0. Okay. So I also have to make a note of to which pins A, B, C, D are connected. So this is DP. Okay. This is G. This is F. This is E. This is D, C, then B, A. Okay. Now, to have 1 displayed, what should I write? DP with 0, G0, F0, E0, D0. B has to be 1, C has to be 1. So what is the hexadecimal equivalent of this? What is the hexadecimal equivalent of this? 0x 0, 0x 06. So whenever I have to display 1, okay, on the SSD, what should I be providing to the port D? I have to provide 0x06. So port D provided with 0x06 will display 1. And on which SSD you have to decide. Okay, depending on your requirement, on which SSD you want to display 1, you can turn on the corresponding SSD. So to display 1 on any of the given SSD, port D has to be returned with the value 0x06. Correct? Now please tell me what is it for 0? How to display 0? Only G will be off. So this is 0, 0, then 1, 1, 1, 1, 1, 1. Correct? So that is how I display a 0. So 0x 7f. Is that 7f? It is 3f. So 0x 3f for 0. Okay. Now like this, what is it for 2? What is it for 2? So I'm making a table for our convenience in our program going ahead. So this is how I display a 2. In case of 2, DP has to be off, then A has to be on, sorry, G has to be on, then F has to be off, then E has to be on, and C and F has to be off, correct. So this is 1, C is off, this is 1, this is 1. So hexadecimal equivalent is 0x 0101 is 5, then 1011 is B. Okay, so that is for 2. Can you help me write it for rest of all up to 9? You can tell me what to write for next 3. So I'm not going to write it down here. Okay, you directly tell me what should I write to the hexadecimal equivalent. So 0x what for 3. So 0x for 3 it is 4f. Okay. So let me write it as 4f for 3. Next for 5. What is it for 5? For 4 it is 66. Okay. 66 for 4. Okay. So you can fill it up later. You can keep it ready till 9. Okay. So it will be easy for us rather than scratching our head. So you can keep it ready till 9. Starting from 0 till 9, you can keep it ready. Now, so this is what I have to be providing to the particular port whenever I want these numbers to be displayed. Similarly, you can try it for some characters, some special symbols, whatever you can get displayed on the SSD. You can have it noted, or you can directly load port D with that particular value when something needs to be displayed. Now let us speak about the direction of these pins. So the 8 segments, okay, have 8 LEDs, 8 individual LEDs. Okay. Now, these 8 individual LEDs are being connected to the port D of the microcontroller. What should be the direction of the pins of port D? What should be the direction of the pins of port B? Sorry, port D. There is in fact an LED connected. So you already know when it is an LED, the pins should be treated as output. So RD0 to RD7 has to be treated as output. Okay, so has to be output. Now similarly, the control lines are connected from RA2 to RA5. Okay, so the control lines are connected from RA2 to RA5. Okay, now what should be the direction of these RA2 to RA5? So what should be the direction of RA2 to RA5? Is it input or output? So to the transistor here, okay, if you take the transistor, so transistor is taking a 1 or a 0 to turn it on or turn it off, right? So transistor will accept a 1 to turn it on, transistor will accept a 0 to turn it off. To the transistor, how is the pin acting? To the transistor, what is the pin acting as? To the transistor, it is input. But if you speak with respect to the microcontroller, what is the direction? So it is always the opposite. Yes, it has to be output. Okay. So all the pins of the microcontroller with respect to the SSD should be treated as output. So RD0 to RD7 will be the data lines associated to the SSD, which needs to be treated as output. And RA2 to RA5 are the control lines associated to the SSD, which also has to be treated as output. Okay, so both of them have to be seen as output. Is that clear? Okay. So I think the programming of the SSD, we will do it in tomorrow's class. Okay. So tomorrow we will do with one program of SSD because it is simple. In fact, okay, let's do two programs on SSD and we will move to the next peripheral, which is nothing but CLCD. Okay. So CLCD, then matrix keypad, then ADC. We will be done with the peripherals. Okay. So we will continue the programming part in the next class, that is tomorrow. So hope today's class is all being clear. We did the configuration of the built-in block of the clock input output, and then we started with the SSD's basic introduction. So we have got the theoretical part known. The programming part of the SSD we will do it in tomorrow's class. Hope the class has all been clear. Thanks for attending the session. We'll continue tomorrow. Thank you all.